Yeah. You think I don't have to say that, but I do. Okay, who can write McLaurin series for cosine of 4x times the square root of x? Who can do that? How do we even start? But we know the cosine power series already, right? So suppose we say, we write the power series for the cosine of x. Remember that was the one that was the even function and it alternated. Let's see if any of you have it in your mind. One. In your mind. Okay, keep going with your mind.
Minus x squared over 2 factorial,
Right.
and then plus x to the 4 over 4 factorial minus x to the 2 factorial.
So in series form, it looks like, let's see if we start with k is equal to 0 and go to infinity to alternate the sign and get the first one positive. I think we could do that, right? So that would be a, oh, wait a minute, let's do without that, right? So the first one's a 1, and now I need x to the 2k all over 2k factorial. Does that look like it's going to work? It gives me a 1 when k is 0. Gives me a negative x squared over 2 factorial. Yeah, that's going to work. Okay, from that, how do I make the power series for the cosine of 4x?
Or you just put the coefficient of 1.
No, because I can't, because it's inside. So I got to put it inside, right? I got to put a 4x inside. Is that okay? I can't just put a 4 here. I got to put it inside the rule. So now we have the power series for the cosine of 4x. We can do term by term substitution. And then we multiply it through by the square root of x. Then we're done. You can distribute that x all the way through and kind of simplify a little bit. If you just leave it like this, I think you're okay. So the key is don't be taking a bunch of derivatives and plugging this into the formula for the Maclaurin series because you got product rule and chain rule and start from a known series and build your way back out.
Is that to the power of root x or multiplied?
It's multiplied, it just didn't fit. Better? Okay.
Multiplied on through it.
Multiplied on through. Yes. Substitution is a term by term operation. Multiplication is distributive. We can't do, if I wanted to do the power series for this, the Maclaurin series for this, I can't just take an infinite series for this one and multiply it with an infinite series for that one. But I do know an identity for that product. We have an identity for this. What's the identity for 2 sine x cosine x? It's the sine of 2x. And then if I move that 2 over, if I want the power series for this, I write the power series for the sine of x, replace each x with 2x, and then multiply the whole shebang by 1/2. So the sine of x was the odd one, right? Sine of x look like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And so in this format, it looked like the sum from k is equal to 0 to infinity. I go minus 1 to the k to get the signs to alternate. And now I need to put my x to an odd power. So 2k will be even, 2k plus 1 then would be odd. So the power series for this one should have a 1 halfway out front here. And now I'm going to replace x with 2x. And there it is. Multiplication is not term-by-term operations. So keep that train of thought and tell me how you would get the Maclaurin series for cosine squared of x. Squaring is not a term-by-term operation. So I can't just take the power series for the cosine of x and square each term. And I can't square something that's infinite. So we got to think trig identities.
Can you split this into like, is it 1 over 2 cosine 2x over 4?
Not the integral of it. Don't give me the integral of it, but what generated the integral. Remember that? But then I have a sine squared. Remember how we integrated this to begin with? We had this identity that was a power reduction formula.
Oh,
It had 2 terms. Not the integral of it.
1 over 2 plus cosine 2 theta over 2.
1 over 2 plus the cosine, here would be 2x over 2. So here we go. I'm going to factor out the 1/2. 1 plus the cosine of 2x. This is what we'll use. Now let's take the power series for the cosine of 2x. Okay, so the power series for the cosine of 2x, I'm putting 2 x's in here. So it's going to be, so let me build it from that. The cosine of 2x equals, I'm going to bump this bad boy over. All right, so the cosine of 2x, I'm putting 2x with a 4x there. So 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. So in summation form, it looks like the sum from k is equal to 0 to infinity, -1 to the k, 2x to the 2k over 2k factorial. That's the cosine of 2x. Okay. Then I want 1 plus that. Well, I don't add 1 to each term. If I have a sum and I'm going to add 1 more item to it, I could just add it to, say, the first term. So now this is a 2. Agree? So now that's a 2. But now I'm going to multiply through by 1/2. So now it becomes a 1 again. So it's back to 1. And then I'm going to put another 2 underneath each of these. Okay, so I can go ahead and put the 2 right there. So it still gives me the same thing, and there's the power series for the cosine squared. Okay, so remember your term-by-term operations, and then you can make these.
Would this make the first term 1/2 though? Or like for the summation?
You can. I mean, it won't, will it? K is 0. Oh, it will make it a 1/2, won't it? Bummer. So I don't want that. Foo. Foo. So I start this at 1 and put the 1/2 out here. Yeah. you can do
Yeah,
that
that's
too.
good.
Let's put a 1/2 out here. So that was like my bonus problem the last time I taught this class on test 3. Would you have thought of that, how to do that?
I wouldn't have used that option. That seems way too simplistic.
Oh,
I
sorry.
feel like there should be like a 50-step.
Probably is.
to integrate it.
Well, then you can multiply by e squared times pi divided by 1 minus the square root of 2
That's what I
to the
was.
0 power. That's 2 to the negative 1. All better?
Yeah.
Don't challenge me, don't challenge me. All right, so did this make you think of anything you saw in your homework problems on web work on section 8.8? Anybody who's kind of working along with the rest of the class? It kind of narrowed it down, didn't it? I understand, you had some busy times and you need to chill every now and then. Okay, so I'm then going to start section 9.1. This kind of essentially is the end of calculus. 9.1, 9.2, 9.3, and 9.4, we talk about vectors. So in section 9.1, we're going to talk about vectors in 2 dimensions. Yes, sir.
Grouping the chapter 8 and 9 together.
No, I think chapter 8 is all, and then the chapter 9 stuff will be on your final exam.
No.
So, but I just thought I'd do something instead of, it's not a good day to go play volleyball today. So we're in chapter 9.
Sorry.
It's when,
It just means the sand would be really clean instead of really hot.
I want it to be sunshiny and, you know. Don't get your hopes up. We're not really going to go to the volleyball.
Dang.
I don't want you to like be the child with Christmas taken away. We're going to keep doing this stuff. Okay, so in section 9.1, everything you ever wanted to know about vectors in 2 dimensions. When we talk about 2 dimensions, we talk about R2, the XY plane. Where have you encountered vectors in your everyday lives? Would you know a vector if you ran into one?
Rowing along sports.
Okay, so you can think about when an object is thrown, it is thrown with a velocity. Velocity itself is a vector. And it follows a path, and that path is determined by the velocities at each point. How much velocity would be the size, speed, and then the direction. Anything in which you have to describe a size, which is called its magnitude, and a direction can be represented with a vector. So velocity definitely is a vector. Force, we talk about force in physics and engineering. You have a force acting on an object, and it's either pushing it up or pushing it over or something like that. So the amount of force and the direction. If you watch a weather report, on a windy day, there's these arrows all over the weather map of Lubbock. The arrows indicate the direction, and then the length of the arrows would indicate the force of the wind. Okay, so vector is any object that can be explained with a direction and a magnitude. Magnitude will be its size or its length. So we have a vector with an initial point heading in some direction, and the direction would be the terminal point. And then we can figure out the length. When I talk about vectors, I can name them from initial point to terminal point. So for instance, I could name this vector PQ, but I have to put the arrow above it so that you know I'm talking about the vector from point P to point Q. In your book, they'll just typeset it in a bold font. For example, the vector from point, say, 1, 3, let's call that point P, to point Q, I don't know, 5, 1, looks like. Let's plot those 2 points. 1, 1, 2, 3, there's point P. 5, 1, 2, 3, 4, 5, 1. There's point Q. And then I put my little arrow that way. We write the components of the vector in these sharp brackets. The X component and the Y component. When we're in 3 dimensions, we'll have an X, Y, and Z component. In n dimensions, we'll have x1, x2, xn dimensions. You're engineers, you'll never get into n dimensions with my physics majors. No physics majors in here? You're a physics major. Why? What made you major in physics?
Oh, I don't know. I just found it interesting.
Yeah, my son did a physics major as an undergraduate. I found it weird. It is interesting. It is. It is interesting. It's very deep thinking. Okay, for this particular example, we find the X component by subtracting terminal X minus the initial X. So in this example, vector PQ would look like 5 minus 1 in its X component and 1 minus 3 as its Y component. So it's the vector whose components are 4, -2. Every vector in the plane is associated with a vector called its position vector. The position vector associated with vector PQ has its initial point at the origin and its terminal point at the ordered pair, 4, -2. And so it would look like this. Count over 4 and down 2. Oops, I missed. And that pink one is the position vector. Associated with vector PQ. It has the same length and the same direction. So in the plane, they would be parallel. The length of this particular vector, the magnitude, of vector PQ is just written in absolute value bars. And sometimes it'll be written in double absolute value bars. I don't know which one your book uses. I think I'll use the double one. It makes it look more like magnitude instead of absolute value. Well, you see with a pair of absolute value bars or double, that doesn't matter, but it's the length. And if I want to find the length of any segment in the plane, I just use the Pythagorean theorem. And that's how we find the length of a vector. I make a right triangle out of this. Maybe I'll go down 2 units and then over what, 4 units. And so this length is 2, that length is 4. And so by the Pythagorean theorem, I take my 2 and I square it, and then I square the 4, and then I take the square root, which is what you would do if you just took the components and squared them. You get the same colors, because the minus sign would be squared. Okay, so in general, the magnitude of vector AB, vector who has those components, is the sum of the squares and then the square root of them. So it's a positive number. So this one is 16 plus 4, This vector has length square root of 20. Magnitude is always positive. You may have also seen vectors written with the I and J notation. The I and J vectors are said to be the basis vectors in R2. The vector I, sometimes you'll see it with an arrow above it. Sometimes you'll see it with a little hat on it. I kind of like hats. I love math because you can put hats on variables. The I vector is the vector whose first component is 1 and whose y component is 0. So it has a length of 1 and it looks like that. Make it big and thick because I didn't grab my colored chalk. So if that looks terrible, let's fix that, make it look pink. So there's the vector represented by standard basis vector I. And then J is the vector going up the y-axis. Right here. And so we use the, if I have a vector AB, we can write that vector as A in the I direction plus B in the J direction. So this one can also be written as 4I minus 2J. Ooh. They're used interchangeably. I don't know, I kind of like sticking things in brackets because it takes less time to write, but it emphasizes a couple of things. One thing is I can take a vector and multiply it by a scalar. And I'm talking about vectors, a scalar is just a regular old number. If I want to make a vector twice as long as vector PQ, but in the same direction, I pick this arrow up and I glue it on here. Or I just double each component in there. So you can multiply a vector by a scalar by multiplying component-wise. Scalar is just a regular old number. So if I take the vector AB and multiply it by the number K, that means each component is multiplied by the number K. If K is a positive number, it makes the vector longer by that scaling factor. If K is a negative number, it'll turn the vector around. So if this is the vector, let's call this vector V, then vector minus V is here. If I plop it on here, this would be vector minus 2V. If I cut it down in half, this is vector 1/2 V. So it keeps them going in whatever direction that K says. Positive keeps in the same direction. Negative flips it around. And if you think about the magnitude of this one, if I go ahead and compute that for you, the magnitude of vector KA, KB, we take the first component and square it, add it to the square of the second component, KA all squared, plus KB all squared. Excuse me, K squared A squared, plus K squared B squared. I can pull out that common factor of K squared and put it right here. So that verifies my claim that it just makes the length a multiple of K, longer or shorter. There is a difference between this and this. This is the scalar 0, That's how many dollars I have in my pocket. This is the vector 0. It's the vector of length 0 and just sits there as the point at the origin. Okay, so this is the 0 vector. And this is a scalar. A unit vector is a vector whose length is 1. So that vector I was an example of a unit vector. And J is a unit vector. A unit vector in the same direction as a given vector well, let's think about it. Suppose I said this is the vector V. It has as its components 12 and 5. That's not a unit vector. What's the length of this vector? 13. I've got a triangle where the x direction is 12, the y direction is 5. So do you know the Pythagorean triple? 12 squared plus 5 squared is 13 squared. Let's put it on the board. Let's see, 144 plus 25 is 169, and that there is 13. So if I wanted a unit vector in that same direction as V, then I got to keep all the signs the same in the x and y component, but I got to scale each component down by a length of 13. So the unit vector in the same direction as V is given by V multiplied by 1 over its magnitude. So in this example, it's just 12 over 13 and 5 over 13, whether you put the 13 in or not. We like to scale things down to have a length of 1. So now if I wanted to find a vector in the same direction as V, but has a length of 8.5, well, I first scale it down to a unit vector, and then I multiply it by 8.5. So I can keep the direction going and make my vector whatever size I want or whatever my needs are. If I want to turn it around, I change the sign on the entire vector, which changes the sign of both components.
Professor Patty, can she hear me? I'm not sure she can hear me.
All right, let's look at adding two vectors together. Let's see, let's take this vector here. We'll put some sort of grid on here. Let's say that this point in the plane is x is 3, y is 2. And let's call that vector v. That would be the vector from the origin to the ordered pair 3, 2. Oops, -2. And then let's take the vector, 4, 1, 2, 3, 4, 5. That vector. That W. W is the vector over 4 up 5. In mechanics, we think of these two vectors, say, acting on an object placed here at the origin. This one is pulling it this way with that magnitude. This one's pulling it that way with that magnitude, and it's going to move. So it's probably going to move somewhere in the neighborhood of here, right? And that's called the resultant vector, or the sum of those two vectors. To find geometrically the sum of the two vectors, we use the parallelogram law. You make a ray from this endpoint, that length. That looks parallel, kind of. Make that parallel, parallel. And then the resultant vector is the diagonal of the parallelogram. So that vector is V plus W. Addition of vectors is done component-wise. You add the x components together, you add the y components together. So in this example, the vector 3, -2 plus 4, 5 should give you 4 plus 3 is 7, -2 plus 5 is 3. So let me see if that kind of looks like, yeah, it looks like it's about 3. 1, 2, 3, 4, 5, 6, 7. My scales are all off. But if you did it on a nice grid paper, that's what the sum looks like. Addition is done component-wise. A1, B1 plus the vector whose components are A2, B2 is the vector. Yes. Yep, I can, thank you. Left, left, that left. Thank you. I can pay attention to that, don't I? I don't know the chat box so that I can see it. Okay, so I try to move it back and forth for you guys, but oh, somebody wanted to see a one more problem. I'll stop early and I'll do that. Because this is really boring, isn't it? Yes,
Can you spell out like the tip to tail addition?
that would be subtraction. Subtraction. If you subtract two vectors, let's look at this one in subtraction. Let's see how much room I've got. Let me get a redraw the picture. So let's subtract two vectors. Here. So for subtraction, let's draw that vector 3, 2. Let me try to make my scale look better. Vector V had components 3, -2. You see that? No, now I gotta move it over to the right. There it is. Okay, and now let's put the vector W, whose components are 4, 5. So 4, 1, 2, 3, 4, 5. So if I want to compute W minus V, I guess I should say V minus W, that's the way it'd be written in the book. Let's go V minus W. Well, that should be the same thing as V plus the opposite of W. So here goes the opposite of W. There's minus W. And now if I do the parallelogram law here, this is minus W, and then make my parallelogram. And this vector here, it's not a good one. Pink, let's go with pink. Would be the vector v plus minus w. Now I can pick that up and it would fit right here. So that is the vector v minus w. From the minus vector back to the v vector. These two pink vectors should have the same length in the same direction. Okay. Guys, can you see that? All right, let me see what else I got. Okay, let's go into 3 dimensions then. In 3 dimensions, we call 3 dimensions R3. And the way we represent the 3 dimensions, we've got, this is the y-axis. Here's the origin, there's the z-axis. And then the x-axis is coming out of the board right at you. We'll poke you right in the head. Here's my, this looks hopefully like it's coming out of the board. And what that, and then I've got the negative z-axis going down here, the negative x-axis going back into the hallway out here. And it cuts the space into 8 octants. There's the octant out here where x, y, and z are all positive, and then where x is negative and y and z are positive, and then where x is positive, y is negative, and z is positive, blah, 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 blah. A vector in 3 dimensions has 3 components, a, b, and c, or the x component, y component, z component. So if I have a vector in R3, it would look something like this. I come out a units or back, depending if a is positive or negative, go left or right b units, and up and down 3 units. So if I want to plot the position vector that looks like 1, 2, 3, I come out at your 1 unit. Then from there, I move over 2 units. And then from there, I go up 3 units. And so there it is right here. Kind of poking out of the board out here. If I want to plot the vector W, that is 1, -1, I don't know, -2. So I come out 1, then I go back 1, and then I go down 2. And so this is still kind of poking out a little bit out of the board. Addition is done component-wise, scalar multiplication is done component-wise. How do you think we find the magnitude in 3 dimensions? Square root of all 3 added together. 1 squared plus 2 squared plus 3 squared. So 1 plus 4 plus 9 is the square root of 14. Addition is done the same way. So in this example, if I add vector v with vector w, I just add component-wise. So I would get 1 plus 1 is 2. 2 plus -1 is 1. 3 plus -2 is 1. So there's nothing special about 3 dimensions, other it's harder to draw. Okay? There are going to be some, we've got multiplication by a scalar, addition and subtraction of two vectors, all done component-wise. But our two versions of multiplication won't be the multiplication that you know and love. So we'll talk about the multiplication next time. I'm going to answer the web work question that was on board. I guess John asked me. I want the first four non-zero terms about zero for t squared sine of 5t. Okay, so we did one similar to that, but let's do that one anyway. It's okay, can I rip this out? Okay. We want Taylor series. For t squared sine of 4t. All right, was the sine the even or the odd one? Sine was the odd one. So let's write the Taylor series, say for the sine of x, or the Maclaurin series. So if it's odd, it starts with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then there's more, but this web work problem just wanted the first 4 non-zero terms. This generates for us a 7th degree polynomial, right? Now we're going to replace each x with 4t. More, but we're only interested in those first 4. And the final step, multiply it through by t squared. All right. Got my t squared. Back in. So what degree polynomial would this be? It's a 9th degree polynomial. So we would call this t sub 9 for this particular polynomial. Okay. Now, what if I asked you to find, using this particular example, this is probably too hard of an example. Yeah, that's not a great example. I'm trying to think of one that was in web work where it asked you to take a derivative of the power series evaluated at a point. Does anybody remember that one? Then I won't tell you now, you'll know later. Okay, so let me see. Do you remember how to make the power series for I can't make a Taylor series for that centered at 0, can I? Because it's not defined at 0. But let's see if we can make a Taylor series for this one centered at X is equal to 1, or C is equal to 1. Did we do that one in class last time? Now, we don't have a formula for this one. So we actually have to take derivatives of it and then evaluate them when C is 1. So let's write out, say, the first 5 terms of this Taylor series. Okay, so the first 5 terms would look like f of 1 plus f prime of 1 over 1 factorial times x minus 1 plus f double prime at 1 over 2 factorial times x minus 1 squared. 1, 2, 3, 2 more terms. I need the third derivative at 1 over 3 factorial times x minus 1 cubed. And then the fourth derivative at 1 over 4 factorial x minus 1 to the 4.
Spot terms, I got a special derivatives.
That's just what I picked. Because I figured I didn't have much board left. All right, so what we need to do is take a bunch of derivatives of this. So let me write that as x to the negative 1/2. Is that okay? So that's f. And now let's get 5 derivatives of it. F prime is going to be negative 1/2 x to the negative 3/2. F double prime is going to be a positive 3/4 x to the negative 5/2. The third derivative is negative 15 over 8 x to the negative 7/2. And now I need one more derivative. The fourth derivative is, oh gosh, 7 times 15 is 105. Positive 105 over 16 times x to the negative 9/2. They're the derivatives I need. Now I need to evaluate each of them at 1. And that's why I chose 1, because 1 to any power is 1. So f of 1 is 1. F prime of 1 will just give me the negative 1/2. F double prime at 1 will give me 3/4. The third derivative at 1 will give me the negative 15 over 8. And the fourth derivative at 1 will give me positive 105 over 16. And so now we're going to fill in the formula. And so 1 over the square root of x is going to look like f of 1, which was 1. Then I'm going to have minus 1/2 over 1 factorial. So over 1 factorial, so we'll put the 1 factorial right there, times x minus 1. Second derivative gives me a 3/4. And then I'll put the 2 factorial right here. And then the x minus 1 squared. Third derivative was negative 15 over 8. And there's the 3 factorial. And the x minus 1 cubed. And then plus 105 over 16 times the 4 factorial times x minus 1 to the 4. Now, I want you to use that, because that wasn't hard to do, was it? especially when you're just watching me do it. Use that power series to write the power series for that. What would you do?
Would you put a 1 minus parentheses?
Put a 1 minus x everywhere the x is. So this becomes 1 minus x minus 1. What does that leave me? A negative x, wouldn't it? Right? That becomes 1 minus x minus 1. So everywhere in here, I'm going to have a minus x when I make that term by term substitution. And anywhere I have a minus x to a even numbered power, I just get the same as if I had x to that power. All the ones with the minus x to the odd power will multiply out to a minus x to that power. But notice the ones with the odd power have all minuses. So all that's going to do when I substitute is put x in the parentheses and change this to a non-alternating series. You agree? And it'll look like this. I gotta smooth it so these folks can see. Other way.
Would it not affect the derivatives?
Would it not affect the derivatives? It would if you started from scratch, but we're not,
Okay.
right? But these numbers will be the same because I would be evaluating. I shifted this one over, right? I flipped it and shifted it. So it'll simplify to that. So we're going to replace each x with 1 minus x, and we decided odd powers, we'll put an x in here and change the sign, and even powers just put an x in there. So this is going to look like 1 plus 1 over 2 times 1 factorial times x plus 3 over 4 times 2 factorial times x squared plus 15 over 8 times 3 factorial times x cubed. Last one is plus 105. That will be an x to the 4th. And 16 times 4 factorial. The reason I wanted you to do that is now I want the power series for this. What do you do there? I already have the negative x. I'm just going to replace each x with x squared. Okay, replace each x with x squared. So this time it looks like 1 plus 1 over 2 times 1 factorial x squared plus 3 over 4 times 2 factorial x to the 4th plus 15 over 8 times 3 factorial x to the 6th. One more guy out here plus 105 x to the squared to the 4th of the 8th. And I was building to my big finish. How do you get that one? How do I get this one from that one? Integrate term by term. The integral of this is that. Integrate each term here. So it'll look like x. We're going to get a constant of integration. I'm going to put the constant of integration first. But the constant of integration, I already know what the value is. I shifted this away from the origin 1 unit. So it's going to be the value of the arc sine when x is 1. What's the value of the arc sine when x is 1? What's the angle that I take the sine of? Pi over 2. So my constant is going to be pi over 2. Okay. And then I'm integrating. So I'm going to get x cubed over 3. So I'm going to have a 1 over 2 times 3 times that 1 factorial x cubed. And then I've got my x to the 5th over 5. So it's going to be a 3, 4 times 5 times 2 factorial x to the 5th. And then I'm going to have 7. So I'm going to have 15 over 8 times 7 times 3 factorial x to the 7. And then the last one, 105 x to the 9th. What is this number here? 16 times 4 factorial? But 16 doesn't sound right. 16 is right. Times 4 factorial. Okay? So this would have been horrible to build from scratch using the Maclaurin series. But this wasn't that bad. It was just substitution and then term by term integration. Okay? All right, thus endeth another week. Any other questions out there? Sure.
That's crazy to do something like flop erasers and stuff. That would suck. All right,
So,
all you.
Thank you. Thank you. Way to go. Into that one. Go into that one. All right, we should have that one. All.
I gotta head to the summit too.
Yeah.